I'm the captain from the space team. Here we have Henrique, RPO, Rafael from ADCS, Rosana from EPS, Arthur from Payload, and Gabriel from Extruders. So today we're going to present our Cansat, the Horizon, which was launched yesterday and today fully recovered, fully functional. And it's really amazing that we were able to launch it and spend the whole night in the field, and it's still working like perfectly. So before we get into the mission itself, we have to talk the vision of our team, which is to make astronomical studies in Brazil available to everyone and disseminate the scientific data that we can obtain during the mission. So thinking about that, the Horizon was built to characterize the atmospheric behavior in Cabo Canaveral and also to analyze the behavior of a 2C Cansat. So to reach our goals, we made our partnership with the Phoenix team, which provides us with the Guara rockets. And was like essential for the whole mission. The mission of the Horizon is in 4 phases. Okay, the first one we have the launch of the Guara and the start of data collection. We also have the transmission of the data beginning in this phase and during through all the mission. After that, we reach the apogee of the rocket in like 16 seconds. And the Cansat is ejected. In the third phase, the satellite begins the controller fall with the opening of its parachutes. And then, in the final phase, the Cansat reaches the ground and is safely recovered by our team.
Think about that, we use the system engineer to develop our projects. Understand all the needs of the mission to find the best solution. For this, we separate the initial requirements and derive them, so that we have more requirements, more specific, that may appear. These initial requirements are given by the regulation, for example, mass, size, and military components, by the launch vehicle itself, and by needs of the operation system. With the system engineer, we are able to understand better what you're making, understand all the parts of the mission, and prevent mistakes before they happen. Prevent that mistakes can appear and vastly change the mission. Here we have a mission architecture with the capital software that we use to make the system-based, the model-based system engineer to understand all the mission and its requirements.
So, talking a little bit about our subsystems, we're starting here with the structures and thermal control. Our structure is designed and printed in polylactic acid, and it has 66 millimeters of diameter and 230 millimeters of height, being a 2C Cansat. Its weight is around 420 grams, and the whole structure is sustained mainly because of the standoff screws, which has four rails around the whole structure. The structure is divided. It has a modular composition, presenting 3 floors. So the first level we have the battery, which is isolated, and then on the second floor we have the PCBs, which contain all the sensors and the electronic parts, and the top level we'll have the recovery system and the parachute. For the thermal control, our biggest concern was because the heat generated for the PCBs could interfere on the battery temperature of operation. So that's the idea of the levels. We could separate the PCBs from the battery, and also the satellite is evolved for this cylinder cylinder envelope, which is hollowed, so it allows some convection of airflow and prevents higher temperatures.
So, talking about our payload, we use a trading studies method to determine which components we would use. With that, we chose to use a barometer and a thermohygrometer to measure temperature, pressure, altitude, and humidity of the atmosphere. Then, we also chose to use a inertial sensor and a GPS sensor. With the inertial sensor, we were able to determine the altitude and then with the location with the GPS.
To guarantee energy efficiency, all the sensors and electronic components were positioned on PCBs and powered by lithium-ion batteries with 3.7 volts and 800 milliamp hours capacity each. And the batteries were also connected to a voltage regulator, which provided a safe voltage for all components. And as the batteries were able to provide the required power for the satellite throughout the mission, the use of solar panels was not necessary based on our power budget.
Regarding to
So thinking about the onboard computer, we choose to use SP32 modular, okay, and because it has a great memory capability, and we needed to use a multiplexer so we could integrate our sensors. And about the communication, we are using a transceiver in the transmitter mode, okay, and we are going to use a helicoidal antenna with an omnidirection partner and the LoRa modulation so we can optimize the distance. Also, all this communication happens in 433 MHz frequency.
regarding to the ground station, we choose to use the Arduino Uno microcontroller and with the transceiver the same as we use in this setup. The measures were received by the control stage route, and we developed a set of
softwares that could analyze the data and then save the data on text documents. We also had live plotting on graphs that we'll show later, and we could see all the data on real time during the launch and the fall of the satellite.
And we also developed the data we saved in a process, and we make a program that we can generate, and we can determine and generate the attributes of the satellites and make a visualization in 3 dimensions.
We'll show it later. So, yesterday, like we said, we had the launch of our satellite with the Czar rocket. It was an amazing launch. The launch was really successful. It was ejected about, it launched, got the apogee and then fall, and about 40 meters above the soil, ground, it ejected, and then the satellite fell, separated from the rocket, gathering different data. Actually, we stopped getting data when the ejection occurred because of the distance from the transmission. here's just our satellite on the field where we got it. Like we said, here we have the graphs that we showed live. Like at the time, it was showing all the data on real time. As you can see on the altitude graph, we have the exact moment of launch. Then we hit the apogee, the moment that the rocket opened its parachute, and then at about 40 meters height, we stopped getting data from the satellite. The same can be seen on the pressure. You can see the pressure graph, exactly the same. And also about the temperature, you can see that it remained constant. Just proving our hypothesis that now is proved now that we have the satellite back, that the satellite wasn't ejected during all the mission, and it was ejected only the final stages above about 40 meters above the ground. So here we have simulation about the attitude. With the initial data we can show you the attitude, the satellite movement during the launch. Here we have first the launch happening. You can see the movements. Just some seconds. Now it hit the apogee and then it turned on, turned on the other side. Right now it's opening its parachute. Open the parachute and starting to stabilize on a controlled fall. So after that, it just landed safely and, like I said, ejected about 20 meters above the ground.
So in conclusion, the Horizon project is not just a project for Earth, it's a gateway to the amazing world of space technology to a lot of people. And we like to thank all our partners and sponsors, of course, LISA, our laboratory, the Czar, our university, the UFMG, of course, our mentor, Professor Dr. Maria Cecilia, and our amazing PO, Henrique, for the amazing job that he did in this project. Also, of course, the Equipe Phoenix for building an amazing rocket that was able to Please, but not less, I'd like to thank you all for the interest in and the opportunity to build this Cansat. Thank you.
So, just to show you guys, we still have the satellite working right here. You can change, please,
I'm going to try to show you all. You can see here, the LASC has a light. It's still working, okay? We also have the GPS. I don't think you all can see the lights that is blinking, but here we have the LED from the GPS. It's also working. And here we are receiving all data.
We're still getting data from the satellite that just landed, so it's still working properly. Thank you all. That's it, our presentation and our satellite.
So congratulations guys, excellent presentation, very nice. I see you also have a live demo, which is great. You are showing real data now. Also, yesterday I was in the LCC, in the launch center, and I saw you guys flying the rocket and also receiving data from telemetry live. And so I saw this yesterday, and today you have an updated presentation with launch photos and launch data. So that's also very nice. In Brazil we have an expression which is like you kill the snake and then you show the stick. It's when you do your job and then you show the results. Well done, so congratulations for this. It's very nice. Does anybody have any questions for the team? Yes, questions. Thank you.
Hey guys, congratulations, very nice project. I have a question about the telemetry, the models, and the range of the telemetry. Our team tried a lot of models with the XSR. You use the same one, but we have a problem with the antenna, so we bought a bigger one, so it solved it. But the little one worked. What was the range you have been tested yet before? What kind of test you did?
We tried to do the calculation and didn't actually get all the distance, so we had to tend the basic parameters on the transceiver, okay, and then the calculation showed that we could transmit in like 2 kilometers. And we did a test on our university. In the test we didn't actually get 2 kilometers because we didn't have the space to do it. So the bigger distance that we got was like 16 meters. No. 600 meters, but it had a lot of trees, a lot of cars and buildings, so we thought it was okay to do it in open fields. And yesterday the Kansat for like a kilometer of the base. I'm not actually sure, but what? Okay, a kilometer and a half was the bigger distance that we got. So we are really happy with the results, and we can show you our codes if you want later, okay?
Any other questions?
Congratulations, guys. I have a question about how do you guys protect it from the water? So we didn't. That was a big worry for our team yesterday because it was raining a lot, and we actually asked the organization if the Kansat had a shortcut while on the ground, if we have any penalization, but they said no, it was okay, so we decided to launch anyways. And didn't have any rain when we launched it, and I don't think it rained at night, I don't know, just the air humidity, but it survived. And we are really, really happy that it did survive.
Yeah, so the presentation looked really smooth, and the project was fantastic. Well done on that. So yeah, behind the scenes, what was your hardest sort of trouble? What was something that kind of you found difficult, your biggest challenges? How did you overcome it? And is there anything you can use from this lesson to implement on maybe a next system?
So we actually have a lot of problems with requirements. So, like we showed, we use the Capella software for the system engineering, but sometimes we're trying to do one thing, and so the system thought it was the best option. The others say no, it was the worst option. So we had a lot of team meetings and spent a lot of hours trying to meet the mid-grounds, and like the PCBs being vertical. It was a lot of discussion, so we could get to that because the onboard computer didn't want a lot of connections, and the extruder didn't want a really big PCB. But we got I think we got the best results after all this meeting and talking and discussion.
Also, it's important to say that that's our first Cansat. We never did it before.
Yes.
It's our first, the first time we built the first time we actually built a project. We won other competitions, but only on like the project on MATLAB and Simulink, all of that. So that's the first time we actually built something. So we had a lot of struggle. We had to learn a lot about programming and computer. We didn't actually know how to use a NAS before, so we learned it. And yeah, we learned a lot and have a lot to make better for the next competitions. We want to improve, for example, our payload, maybe use a camera and other stuff like that. So have a lot to improve, but actually I'm really happy with our results.
Yeah. Any more questions?
Hi guys, congratulations on your project. I was a little bit confused on why did you guys choose to use a multiplexer on your subsystems. Could you explain me a little bit about that?
Okay, of course. So the SP32 only has like two. Yeah, we can use one sensor with the codes that we're building. Could only use one sensor with in the IC enters. So we could make another code, but like we said, it was our first Cansat. So it was really complex at the moment. So we thought it was simpler to just put another component. Okay.
Well, it's a very nice presentation, very beautiful, and I like to do beautiful things, so it's something to say. You reached a new achievement in the simulations and real-time data processing. It's really impressive to see what you got from yesterday to today. So congratulations and very nice for you. That's it.